now 150 billion per year industry, growing at 30% per annum. It's even growing in the UK. There was almost no usage of solar energy back in 2000. There are now, even in the UK, which doesn't have the world's greatest sunlight, there still are quite major solar farms that have been introduced. And on the right here, we see a graph of the growth. You may not be able to quite see that, but it's rapid growth, particularly rapid in China, United States, and in Germany, but growing in most nations around the world, and obviously a huge potential for this technology in the Caribbean. And if just look at the cost in regions where, in sunny regions, PV power, solar electricity is cheaper than electricity generated by coal or gas. And also just look at how the cost has been driven down. We're plotting here the cost silicon PV cells, and it's fallen dramatically over the last 20 years. So, as I said earlier, research into the fundamental science and technology has really borne fruit here. So what are some of the challenges with solar cells? There are many. We need to continue the cost reductions and enhance the efficiency. We need to balance systems and installation cost. That's a really important kind of aspect of deployment. We need to integratable PV products, and we need, very importantly, to integrate the energy storage, integrate the generation with the storage strategies, and to develop this a real challenge, particularly I think for the chemist, solar to fuel pathways, and many challenges here that we're just going to look at briefly in a few minutes. But the community is responding to these challenges. There's some really neat materials engineering in recent years in printing solar cells from a variety of materials, rather simple preparative processes from solution, but you can generate this whole range of simple, easily deployable devices which are lightweight, cheap, and low embedded energy. So again, a really strong area of progress. Just look at some of the materials that are used, very wide range of materials. One very extensively investigated, a dye-sensitized titanium dioxide. Titanium dioxide, a common cheap material, and we can improve its performance by coating it with dyes that absorb the sunlight. TiO2 is slightly too high a band gap for optimum efficiency. We can use a whole range of organic materials, so very creative organic chemistry in this field, and then a real breakthrough in recent years in these perovskite structure materials. These are fascinating systems where you get large organic cations propping up this structure, and they then have very high efficiencies. And then you can print these materials, as I've said, on, for example, here, you're printing one of these perovskite systems onto a steel printed module. And successful startup companies are developing this technology. Let's though think a little bit about solar to fuels, because in many ways, scientifically, this is one of the really major challenges. Now, as I said, evolution learned how to do this over billions of years. The photosystem responsible for photosynthesis is an absolutely fascinating piece of photochemistry. I can't go into the details, but it really is stunningly clever in many ways. Probably less efficient than solar PV, but evolution has made it as efficient as it needs to be. But we need to develop artificial photosynthesis. We need to be able to take the energy from sunlight and convert it directly to fuels. And if we can do that, there's a huge advantages, particularly if we can generate solar hydrogen, if we can split water directly into oxygen and hydrogen using sunlight, because then we truly have green hydrogen. I'm going to come back to this in a few minutes, but in fact most of the hydrogen we use today is not green hydrogen. Once we do that, well, there's lots of great chemistry we can do. We can react hydrogen with CO2 using a catalyst to make methanol. And yesterday afternoon, we heard a beautiful talk with very novel chemistry to promote this key reaction. Once we've got methanol, methanol itself is a good fuel, but also we can use catalytic chemistry again if we want to reforming catalysis to separate out the hydrogen, then feed the hydrogen into a fuel cell. So some really, really interesting and important challenges here. And in fact, there's a kind of fascinating range of things we can do in the solar to fuels technology pathway. If we've got sunlight, water and carbon dioxide, we can develop, for instance, carbon-based fuels. We can do it in a number of ways. We can, just as I've been describing, we can photolyze, use the sunlight to split the water into hydrogen and oxygen, then react the hydrogen with CO2 to make the carbon-based fuels. Or we can use the sunlight to make electricity. We can then use the electricity to electrolyze water, and again we've got hydrogen, CO2, we can go to fuels. Or we can take the electricity and electro-reduce CO2. We can add the electrons onto CO2, we reduce it then and end up with carbon-based fuels. Or perhaps the biggest challenge is to go directly, is to take CO2 and convert it directly into a carbon-based fuel using the energy from sunlight. And there's research around the world on all these pathways. And in fact, the viability of them has been explored in a couple of, I think, really rather authoritative reports from the Royal Society Policy Team on green hydrogen and carbon utilisation. So you may wish to follow those up. Let's just look at some of the materials devices for solar-driven water splitting. There are three general approaches. The first, I'm going to say a little bit more about in a few minutes, is to use photocatalyst suspensions. Essentially, you have a material, you excite electrons in that material, the electrons then reduce the hydrogen, the holes that are left behind oxidize the water to oxygen. We can do something, actually a fairly similar job in this electrochemical device where we've got a photoelectrode, or we can just generate electricity, as I said a few minutes ago, using our sunlight, and use the electricity to electrolyze water. Here are some of the materials that are used. As I said, dye-sensitized titania, these beautiful conjugated polymers, or for the photoanodes, we use these oxide materials. Just a few words about the metal oxide photoanodes. A great deal of very nice materials chemistry research on these systems here is nanostructured iron oxide, titanium dioxide, bismuth vanadate. So a real area for the creative solid state chemistry. Now I want to take one particular aspect, because I'd like to say a little bit about my own research, and this relates to hydrogen production by photocatalysis. That's the first of the routes that I outlined just a moment ago on the previous slide. Now, the first point to note is this rather sobering one. We talk about hydrogen as a green fuel, and of course if you burn hydrogen, you don't get CO2, you don't get nasty gases like nitrogen oxide, so in that sense it is a green fuel, but in another sense, at present it isn't, because only about 5% of commercial hydrogen comes from renewable sources. Most commercial hydrogen, over 90%, is generated from fossil fuels. A high proportion, in fact, is generated from essentially catalytic reforming of methane, of natural gas. So really green hydrogen, we need to shift this. We don't want to be generating our hydrogen from fossil fuels. Electrolysis I've talked about already. It is becoming competitive, but there are issues here. Photocatalytic conversion, there's been intense research done for the best part of 40 years. Now, the particular example I'm going to give you that shows that these systems, these are gold palladium nanoparticles, can be really efficient for photocatalytic hydrogen production. So it's quite a nice illustration of how nanoscience, both experimental and computational, really can have an effect in this field. I should just actually go back. Say I'm going to be talking about the modelling work, and this was very much undertaken by this guy here, Andy Logsdale, and a student, Chris Downey. So just let me try and explain, apology to the kind of non-chemists or physicists amongst you, but how do these co-catalysts work? What you have is, you have a material, TiO2, and you sensitize it with a dye, and that absorbs the sunlight. And essentially what it does, it excites electrons. And what you want to do is you want to separate the electrons from the holes which they've left behind. One of the big problems is that you get recombination, and you want to prevent that from happening. So what you do is you decorate your titanium dioxide with these nanoparticles, and what you're hoping that will happen is that the electrons that you've excited will go onto the onto the nanopart. Sorry, here's the nanoparticle. That they will go onto the nanoparticle here, and once they're on the nanoparticle, they're separate from the whole states, and they can affect the reduction of water to hydrogen. So you add your electrons there, and you can create the hydrogen. So essentially, the role of this co-catalyst, this is this nanoparticle sitting on the surface of TiO2, is to capture the electrons, which then affect the reduction to hydrogen. Now, you can use gold. Gold is quite widely used. It's very widely used now in catalytic science. You can use gold, and it works. If you alloy your gold nanoparticles with palladium, the efficiency increases dramatically. So here are your gold palladium nanoparticles, and there's some data down here just showing you make these alloys, and the efficiency increases very rapidly. Some really elegant experimental work by our collaborators in Denmark. Now, this is where the computation comes in. I'm not exclusively, but mainly a computational chemist. So what we did was a series of high-quality calculations where we looked at how the electrons were distributed in these nanoparticles. So here's our model for the nanoparticle, and what we found is that in these gold palladium systems, particularly when the palladium was separated so that it coated the surface of the nanoparticle, the electrons were highly concentrated on individual sites. So they're highly concentrated on individual sites, and that assists, we argue, their ability to reduce the water to hydrogen. So there's a lot of more detail in the electron structure, but we've used here high-level computational methods. They've told us how the electrons are distributed on this nanoparticle. That helps us to understand why it works so well as a co-catalyst in this system. Well, I'm going to move on now. I hope that's given you some glimpse of the current status of research into solar energy systems, particularly the challenges posed by the development of solar fuels. But it's an exciting area, and an area that's making really very rapid progress. A lot of work all around the world. So let's now move on to my second technology, which are high energy density batteries. So what are we about here? Well, essentially, this is about exploiting solid state chemical reactions to produce electrical energy. And the absolute classic example is this one here, lithium, that very simple solid state chemistry, lithium reacting with cobalt oxide to make this lithium cobalt oxide system. And you can use that reaction in an electrochemical cell. Here's your lithium anode, here's your CO2 cathode, and when you discharge, electrons go around the circuit and lithium ions move across. Now, that chemistry electrochemistry was developed by John Goodenough, absolutely fantastic science, when he was working in Oxford around 1980. I was a young research worker then, essentially a postdoc. I didn't actually work with John on this, but we knew the work was going on, and it really was fantastic. Nobody, though, it's a really interesting example of the impact of science. Nobody realised how this technology would be deployed, that in fact it's changed the way in which we live. These devices that we all spend too much time looking at wouldn't be possible without this very basic electrochemistry developed by John Goodenough, getting on for 40 years ago. John has continued, he's now back in Texas, and he's continued to make really groundbreaking contributions to this field over a very long career. Just a little bit of history of batteries. I mean, it's a fascinating bit of the history of science. Origin of batteries, the first origin here is Galvani. Galvani did these experiments, it really is absolutely amazing, when he put pieces of iron and copper against the muscles in frogs' legs, and he saw them twitch. And he thought, it's the twitching muscles are producing electricity. So anyway, then Volta comes along and shows that this is wrong, in fact, that what is happening is this iron-copper coupling that's producing the electricity, and that's what makes the frog's legs muscles twitch. But that was the foundation of battery technology, because Volta built on that. He built his famous voltaic pile, stacking zinc and copper metal discs, separated by cloth soaked in an electrolyte. And I used to work at the Royal Institution in London, and we had an original voltaic pile that had been given by Volta to Faraday, because Faraday, in my view, possibly the greatest experimental scientist of all time, he needed Volta's technology for the subsequent fantastic discoveries that he made. Without Volta's battery, without the voltaic pile, Faraday he couldn't have founded the science of electrochemistry, which he did. He couldn't have done his groundbreaking experiments on electromagnetic reduction. But Faraday definitely, because he had the voltaic pile, he's the founder of modern electrochemistry. The other absolutely amazing achievements, all this is in the first half of the 19th century, was made by Humphrey Davy. Humphrey Davy used the voltaic pile to split common compounds and make new elements. And about 10 of the chemical elements, sodium most famously, but sodium, potassium, rubidium, and some of the 2A metal elements were in fact first isolated by Davy in this first half of the early part of the 19th century. Absolutely amazing stories in the history of science. Here's how batteries has developed. Battery technology has developed over a couple of hundred years. We start off with Volta, then in the late 19th century we get lead acid batteries that are still with us today. Then later we get the nickel cadmium, steady progression, but now all the big effort in battery technology is in lithium ion. And the field has progressed very, very dramatically in recent years. Here we're plotting some of the key things, energy density, specific energy here, and you see that these lithium ion systems really outperform all the other available technologies. So as we say here, it's probably the greatest advance in electrochemistry over the last century, and groups around the world again working intensively in this field, and it is very, very topical indeed. What I've done here is taken a few press quotations. You can have a look at them. Battery technology will define the future of renewable energy. Batteries are the next frontier of industrial competition. Here's some anxiety. Germany lags behind in battery race. Spiral environmental costs, that's something we need to think about of lithium batteries. But this is a hugely, hugely topical area. In the UK, our government has recently invested £500 million, something like $600–700 million, in a major research program in high energy density battery technologies. So let's again just look briefly at some of the challenges, the material science challenges. The cathode. Electrochemical devices have anodes and cathodes. The key one in these systems are the cathodes, and those are usually transition metal oxides like the cobalt oxide that Goodenough developed in his pioneering work, but then some layered structured materials and also phosphates and silicates. And in fact, these phosphate and silicate materials again were pioneered by John Goodenough, amazingly creative man. Electrolytes, the electrolyte in your battery in your mobile phone is essentially a liquid device, which is in some ways less than ideal. So there's a big push to develop solid state electrolytes. So let's just look briefly at some of the cathode materials for lithium-ion technologies. Here I'm going to highlight the work of Saiful Islam. I didn't play any role with this. I can claim some very distant connection because Saiful, a very successful scientist now, was one of my early PhD students, and he did some early work on modelling battery systems with me for his PhD, but he's gone from strength to strength since then. Anyway, what is the challenge? Energy and power density, materials cost, safety, that's one of the problems with the cobalt oxide systems, toxicity, another problem with the cobalt oxide systems. So here are some of the materials that are being used. There are these lead oxides, there are these spinel oxides, then there are these polyanion types, these phosphates and silicates. I love showing these pictures. I spent quite a lot of my life as a solid-state chemist, so I love these crystal structures, really beautiful structures. So these are the materials that are being actively investigated, particularly at present these, the layer-structured oxides, which are getting higher and higher performance, but also these phosphate and silicate materials. But I'm going to say a little bit more about the solid electrolytes. Can we get solids that conduct electricity, conduct essentially ions, rapidly? And here again are some of the very, very interesting materials that are currently being investigated. Here are some of the issues. We want high ionic conductivity. We need the transport mechanisms that facilitate that. But as I'll show, we can have problems with materials due to processes taking place at interfaces and at the boundaries between the different grains in the material. So here are some of the systems. Garnets, these essentially are highly complex systems related to silicate materials, these anti-perovskite lithium chloride, and these what we call lysicon type materials, which can be sulfides or they can be oxide systems. So I'm just going to give you one example here, what I think is really nice recent research. Again, apologies for the non-chemist, but maybe you'll just get a little bit of feeling for what is going on here. These are lithium silicate, lithium phosphate material. Now these oxides are stable, less air sensitive than sulfides that have been widely used, but they have lower conductivity. And if you look at lithium silicate itself, or lithium phosphate itself, they're rather poor ionic conductors. This wasn't particularly understood. But if you look at solid solutions, so if you make a compound that essentially is a solution of the silicate and the phosphate, you get much higher conductivity. So can we understand that? Now here are these crystal structures. Again, I love showing these. They have rather different kind of lithium distributions. These ones have full occupancy of the lithium sites. These have only partial occupancy, which is a significant factor. But then my colleague Saiful Islam is able to model the lithium ion transport, the rate of lithium ion transport, in fact the conductivity. He can model that as using computational methods as a function of the phosphorus to silicon ratio. And you see that the conductivity, this is a log plot, the conductivity goes up in the middle, and that experimental observation is beautifully reproduced by these calculations. You can then go further and look at the mechanisms that are leading to this enhancement. So this is, in my view, a really creative piece of experimental and computational solid-state science. Then I'm going to show you a bit of real materials science, and these are grain boundary effects. So this is a candidate solid electrolyte, this lithium oxychloride. Here it is. It's got what we call the anti-perovskite structure. It's got some good things about it: high ionic conductivity, low barriers for the lithium migration, very low cost materials, but it's got what we call grain boundary resistance, and that hasn't really been understood very well. So what's a grain boundary? Well, most materials that we use in these batteries are polycrystalline materials, so with lots of small grains, and you get a boundary between the grains, and that can provide a barrier to the conductivity. Now what this really nice work did was to model this whole process. So this work actually constructed, very, very clever work, an atomistic model for this grain boundary. Here it is. It then calculated the energy, showed that these energies were low, and that's why you get a lot of these problems in this material, and he was then able to calculate the conductivity and obtain reasonable agreement with experiment. So he's understood the origin of this low conductivity is to do with these grain boundaries. Once you know the origin, you can start to try and do some materials engineering to mitigate the problem. Right, well those was perhaps again just some glimpse of some of the materials, problems and issues with battery systems. Again, a lot of exciting work around the world and huge and very rapid progress. Let me go to my third technology, and that are fuel cells. So what's the concept behind a fuel cell? Fuel cell essentially you're combusting fuels to produce electricity. So you're burning hydrogen or hydrocarbons to produce electrical energy. So these are some of the kind of very basic chemical reactions. Sorry, I should have a 3 there. Basic chemical reactions, but essentially you're doing this combustion in a way that generates electricity. The work I'm going to talk about here highlights a good colleague of mine, John Irvin, at the University of St Andrews. So fuel cells, as I said, they're electrochemically combust fuels. They have high efficiency, 70% chemical to electrical. That is really high efficiency. They're very scalable. We can have small or very large scale systems. We've got a lot of flexibility on the fuel. They're silent, they're clean, and they give quality power. So they've got a lot going for them. Let's just look briefly at how they work. This is a solid oxide fuel cell. So it has all its devices, the electrodes and the electrolytes are solid materials. And here, let's just see how it works. Here's cathode, electrolyte, anode, and we'll see it working here. Can you see the air comes over the cathode? Sorry, the oxygen comes over the cathode. It's then reduced to oxide ions by electrons that are flowing around the circuit, and the anode we produce the hydrogen. So essentially what we're doing here is, reduce the water, excuse me. So oxygen here is incorporated and water there comes out. So essentially we're burning hydrogen and oxygen to generate water, but we're doing it in this way that generates electricity that flows around this circuit. And interestingly, that's why I got confused a moment ago, we can do the process in the reverse. We can essentially apply a voltage and then use that essentially to split water. So this is doing the reverse process. Now we're taking water, splitting it into oxygen and hydrogen. So we're applying power and generating oxygen and hydrogen. So we can work this the two ways around. We can have a solid oxide fuel cell, or we can have an electrolysis cell. Now this is real technology. Here is a large-scale installation in London, near King's Cross in London. Solid oxide fuel cells running on natural gas and on biogas. So what are the challenges? Well, this is probably the top one, is the biggest. Endurance. The materials in fuel cells have a tendency to degrade, and that has held back the technology, but this problem is slowly being overcome. You need high performance, and so there's a huge amount of work on nanomaterials. We do need to develop new materials, but their implementation can be difficult. And that often is a problem in materials science. You can develop new materials, but sometimes their implementation is problematic. I can only give you a glimpse of some of the really fantastic materials chemistry that's going on here. We have these nanostructured electrode materials using a whole range of oxides, some rather simple oxides, complex oxides that you essentially blend together. Here you've got these perovskite titanate backbones with an yttria stabilized zirconia backbone. You have to combine these all together in a robust, viable device. We can see actually some of the electron microscopy of these systems. Here's the electrode, this really rather complex system, lanthanum, calcium, nickel, titanate. So this brings out all the versatility of solid-state chemistry, interfacing smoothly with the electrolyte. So a lot of really challenging solid-state and materials chemistry there. But again, really substantial progress being made around the world. Now, my fourth and last technology that I'll go through fairly quickly because of time are thermoelectrics. So what the thermoelectrics do, they convert, these get less attention than the others incidentally, they convert waste heat into electricity. Now, it's a really, really valuable thing to be able to do. So what you have is a heat source, a heat sink, but you couple them by two semiconductor devices. One is a P-type semiconductor, one is an N-type semiconductor, and by this way you can convert a lot of the heat energy into electricity. You can do this power generation mode. So it's a simple concept, simple device. Essentially you're taking the energy from the heat and by this rather clever procedure you're converting it into electrical energy, and it's been known for a long time. The Seebeck effect, which is essentially the thermoelectric effect, was originally discovered by Faraday, who I mentioned earlier, such a fantastically versatile experimental scientist. The reverse process, the Peltier effect, that I'll look at in a few moments, followed fairly soon. And this, of course, is all about movement of charge in a thermal gradient, and then related technology of thermocouples, originally developed in, again, around the same time, but then Johnson Matthey produced the first commercial devices in the late 19th century. So let me just remind you what the principles of thermoelectricity. As I said, we have the Seebeck effect. That's taking the heat, taking your waste heat, coupling your heat source to your heat sink via these semiconductor materials, and you generate power. Now you can make it work the other way around. You can make it work in refrigeration mode. That is, you apply power and you can pump heat, pump heat out of your target system in order to achieve active cooling. So we can have, I'm going to concentrate on this, but remember we can work this the other way around, just as we could work fuel cells the other way around. And there are a lot of applications of thermoelectrics. They're used in these kind of space exploration, planetary exploration devices. They're used increasingly to harness the waste heat in homes, in buildings, and in automobiles. So this again is a growing technology, even used to power watches. So what are the opportunities? Very, very substantial and growing. Exhaust heat recovery for fuel efficiency in automotive devices, heat recovery for powering electrical systems in aerospace. I'll not go through all these. Heavy-duty marine heat harvesting, personal and space cooling if we use the Peltier effect, recovery of heat in intensive process industries in manufacturing, combined heat and power, solar heat harvesting. So a lot of potential applications. But there's a really urgent need for improved efficiency of the materials. Now, again, I can't go into detail, but I'll just introduce you to the key concept. The key factor in thermoelectric materials is what we call the figure of merit, ZT. Now, I'm not going to burden you with this, but just notice two things it's got. It's got the conductivity of the material, that's the electrical conductivity, and then it's got the thermal conductivity. And what you want, therefore, is a material with high electrical conductivity. You want it to be a good conductor of electricity, but you want it to have low thermal conductivity. It's got low thermal conductivity. The heat won't pass through those semiconductor systems. It'll be converted into electricity. So all the work relating to optimizing materials for thermoelectric applications is focusing on these two aspects, conductivity, and particularly on minimizing the thermal conductivity. So what are the challenges? This is work we've been doing in collaboration with Steve Parker, University of Bath, and Robert Freer at the University of Manchester. So I wanted to highlight Robert's contributions. You need these new materials with higher average ZT. You need to be based on lightweight, and let me underline this point, earth-abundant materials. You need cheaper materials. You need to look at a wide range of systems. Again, rather like the batteries, you need to know what's going on at interfaces and grain boundaries, and you need to be able to design and synthesize new materials. Now, a great deal of activity here. What I'm looking at here are some of the materials that are being investigated. Now, I'm sorry if this slide is too small. The really good ones are over here. And I just have to tell you, those really good materials, they contain, on the whole, very heavy elements. Materials with the heavy elements tend to have the lower thermal conductivity. So they contain elements such as tellurium and bismuth. Bismuth telluride is a very good thermoelectric material. Now, that's fine. The problem is these are not earth-abundant materials. What we're showing you here is essentially a plot of abundance for various metals, and the ones that are used that work really well in thermoelectrics tend to be the ones using the elements here, such as bismuth and tellurium. What you want is to be able to build them out of the elements over here, like titanium, silicon, oxygen, etc. So that is one of the real challenges. It's a challenge that hasn't been fully met yet, but there is progress being made. Well, the last thing I want to talk about is the whole question of hydrocarbon fuels. I've talked about renewable energy technologies, but almost certainly the world is going to continue to use, to some extent, in some applications, hydrocarbon fuels. So we need sustainable, renewable hydrocarbon fuels. Now, this is a whole topic on its own. We could have several additional lectures. One aspect, of course, though, is the need, for carbon dioxide capture and utilisation. That is one of the grand challenges faced by chemistry in the next 20, 30 years. Can we effective methods for capturing and then utilising carbon dioxide? And again, we heard a beautiful talk yesterday, as I mentioned earlier, about reacting CO2 with hydrogen to make methanol, but I'll just give you a glimpse of this field. Now, CO2 does offer the possibility of providing a carbon feedstock. If you look, a lot of our materials that we use, and most of our fuels at present, are carbon-based. Now, in the future, at present, those carbon-based systems derive from petrochemicals. Now, that's going to have to change, so we will need alternative carbon feedstocks. And CO2, if we do clever chemistry, can be rather a good carbon feedstock. So what I'm showing you on this slide are some of the things we can convert using chemistry that we know about today, that we can convert CO2 into. I'll not go through them all. Formic acid, carboxylic acids, ureas, carbamates, organic carbonates, methane, hydrocarbons. So CO2 is an unreactive inert molecule, but with clever chemistry and with supply of energy, we can convert CO2 into lots of interesting, much more interesting carbon-containing molecules. So what are we trying to do here? We're trying to take CO2. We will need to capture CO2. That's a whole different and really rather challenging and difficult area. We then want to convert it, store it, and use it. And this technology will rely critically on catalytic science. Some of the work I'm describing here has been done by Alberta Roldan at Cardiff, working with Nora DeLu, and I had some role in the earlier stages of this. So what we're going to try and do is we're going to try and get efficient CO2 reduction at mild TP, temperature and pressure, just as we heard yesterday afternoon, and we want to do this using cheap building blocks. So I'm summarising here actually an all very large scale project that's aiming to use CO2 conversion at moderate temperatures and pressures. It had computer-aided design of new sustainable catalysts, synthesis of these materials, electrocatalytic testing, design of a photocatalytic reactor, and then detailed life cycle analysis to show that this whole makes sense economically and environmentally. It took its inspiration, this work, from nature. This is an enzyme, a hydrogenase, and it has at its core this cluster of iron and sulfur atoms, an iron-sulfur cluster. Really, really interesting. And you can get very, very similar geometrical features on the surface of this iron sulfide. It's an iron sulfide known as greigite. So what Alberto Roldan and other people working on this did, said, well, let's see if we can get this material to behave as a decent catalyst. There's an enzyme here that works as a decent catalyst. And they did some very clever computational chemistry. They looked at how CO2 was absorbed on the surface of this material. They showed that this configuration here, where it's also reacted with water, is particularly stable. They were then able to interact with the people doing experimental work and show that we got viable routes here to react CO2 with hydrogen to form formic acid or to react it to form methanol. So here you really are converting CO2. Now this is demonstration work. It's not kind of commercial, industrial level, but it's showing that the creative chemistry we can do to utilize CO2, and much, much more work needs to be done in that area. Well, I think I've more or less finished now. So what is perhaps this is the most important slide, the whole lot over the last 50 minutes or so, one of my conclusions and perspectives. The sustainable global energy supply, let me just underline this, a sustainable global energy supply, that's what we need. It's achievable given the continued substantial investment in the underpinning science, energy and technology, but also given political and societal will. And the last part is absolutely crucial. If we're going to stabilize this problem down here, this is the mean temperature variation that I showed you right at the beginning. This is what we need to do. We need far more than just the underpinning science. There's lots of societal work to do, but we need investment in the underpinning science, engineering, technology, but we really need the political and societal will. So thanks a lot for listening to me, but let me just highlight the people who've contributed slides, amongst other things, but they're intellects as well to this work. Jean-Marie Tarascon from the Collège de France, who's one of the leading people worldwide in the development of battery technologies. Colleague James Durant from Imperial College, very leading figure in the field of solar fuels that I was talking about. Saiful Islam, who works mainly on the battery materials, but particularly developing computer models to understand the battery materials. John Irvine, one of the really leaders in the field of developing materials for fuel cell technologies. Robert Freer, very much on the thermoelectrics, and then Nora DeLu, and Alberto Roldan, who undertook the work on the CO2 conversion that I talked about at the end. So, just to conclude, I've gone through a lot of material. I hope it's given you some feeling for for the way in which these renewable energy technologies are developing, and again, some feeling for the challenges but opportunities in developing new materials that really is going to make these deployable on a large scale. So, thank you very much for listening.
We have time for a few questions, and I'm sure after that whirlwind tour, we have an exam at the end as well. All right.
Yeah, happy to take you an exam, yeah.
So,
Tara.
can I ask you to step up to the mic and introduce yourself when you're...
That's good. Richard, it's a very good talk, very excellent. Lots of information. I'm just wondering about what happens to the dye sensitized. Michael Gretzel did, and there was a lot of promotions, and then a few years back I heard that Japanese are making a breakthrough by a very innovative idea of polymer material. Yeah. And then suddenly everybody is looking for perovskite. So it just died?
I mean, no, the dye sensitized materials are still, they are, I don't think, well, I can't speak with authority,
Yeah.
but let me say, I don't think they're ever going to become large-scale technology. But I think they will have niche applications, for example, in those kind of portable printed devices I was talking about, that I think they could be really significant there. The kind of more fundamental areas of solar energy research really have been very, very dominated, as you were saying, in the last 5 years, by 5 or more years now by the perovskite systems. These hybrid perovskites discovered by Henry Snaith and other people, which do have these dramatically improved efficiencies of over 20%. But I think we need a word of caution. Now again, I can't speak with total authority, but the perovskite materials do have a lot of challenges. They have a lot of challenges of stability, stability particularly, for instance, towards moisture. They may even have problems of degradation when they're exposed to sunlight for long periods. Now, there's a lot of work on those, but again, the jury's out as to whether the perovskite materials really are. I'm sure they'll have applications. Whether they're going to become really large scale, again, I think the jury's out. But anyway, the original answer, I think, the dye-sensitized materials, yeah, still good, in fact, absolutely fascinating chemistry, still good systems, niche applications, probably not much more though.
Yeah, but the efficiency was low anyway. Well,
The efficiency is low.
20%.
Efficiency was low.
Now, of course, the tandem systems are very, very
Yeah, that's right.
popular.
Yeah.
And used in NASA.
Yeah.
With a 40% efficiency in a recent
Really as high as that?
paper,
40?
paper came out.
No, I didn't know that at 40%. I mean, that's amazing if it's true. Yeah. And of course, you're going to enhance the efficiency of the dye sensitized, as I mentioned briefly, by the use of these co-catalysts. And that really is, if you're doing them for instance, as we say, for hydrogen production.
But I'm worried about the energy storage problem, because we have got green energy, the zero energy building, but the storage of the energy is really expensive.
Storage.
4 or 5 years you have to change the battery. It doesn't make sense. And it's all using the smart grid. Everybody is using.
Yeah,
So,
I mean, you're absolutely right. The storage is a major problem. Certainly the current generation of high energy density batteries is not sufficient. I mean, that's why, well, not the only, it's one of the, if you look at why there's this huge investment, a lot of it is driven by electrification of transport. But also it's driven by the need to get much higher energy density. But that field is progressing. If you look at the energy density of lithium batteries, it has improved very considerably over the last 5 to 10 years. Now, whether it can really get to the levels that you're going to need for energy storage, I mean, there are kind of other ways you can perhaps think of storing energy, but it would be best if you could do it with these battery technologies. Whether you'll be able to achieve that, I don't know. But it's a good target particularly for materials research. Oh.
Beautiful talk and very comprehensive coverage of issues and opportunities. I will be giving a talk this afternoon, as we talked about, where our focus has been application of nanomaterials to address many of these issues across the spectrum.
Yeah, if I can just say, I mean, that's...
You mentioned there in your presentation that is one of the directions that you think, there are opportunities. So could you give me your perspective?
Absolutely, and perhaps I should have emphasised that more, so I'm really glad you raised it. Development of nanomaterials, I mentioned it probably very briefly in the context of the battery systems, but it's really important there. A lot of work worldwide, and also very, very important for the fuel cell materials. I really couldn't go through it, but there's beautiful work by John Irvin, whose work I did try to highlight, on showing how you can improve the performance of fuel cell materials by using nanostructured systems. So, looking forward to your talk, but thank you. That is a point that really does need to be emphasised.
Right. I think we need to wrap up, but before we shut down, let me just remind people that this talk was sponsored by New Forest Energy Technologies, and we would like to present a small gift on the behalf of the committee.
Thank you very much indeed. Thanks.
I should have noted as well that Professor Catlow has over 800 publications. He's the Foreign Secretary for the Royal Society. At one stage was working at the Royal Institute. He's mentioned Michael Faraday several times. I must tell you about the connection with Michael Faraday in Jamaica as well. All right.
You should tell us now.